Hello. Measuring dryness fraction is an important thing, and the principle on which this measurement is done is interesting, and that interesting principle is what I would explain to you in this video. As you know that dryness fraction is mass of dry steam upon the total mass of steam. It measures the fraction of dry steam in the total mass of wet steam. Okay, so that's dryness fraction. If you it can be expressed in percentage points. So this ratio multiplied by 100, it's in percentage. So you can say steam is say 90% dry. That means the dryness fraction is 0.9. 80% dry, dryness fraction is 0.8. Okay, how do we measure that? One simple principle that is used is separate the water particles from the wet steam. How can we do that? The principle could be simple. Take the sample of steam from the steam mains, that's a pipe which carries steam. Take out some sample, let the steam be subjected to, create some kind of obstacle in the flow of steam. So water particles would hit that obstacle, some plate which you place, water particle can be collected, you measure that, you can weigh that, the steam would bypass that obstacle, the dry steam, and then you can condense the steam, measure that steam, that would be dry steam, and then you can find out, and you have already measured, one can imagine the process something like this. You have let's say this is a device through which you pass the steam. You create certain, there is some, you can show there is some obstacle in the passage of steam, and the steam will hit that plate. Let's say it would trickle down, the water would trickle down. This could be measured, and let's say this is water. Remaining steam which is leaving this device can be condensed, and that can be measured. So if that condensed steam will be, we assume it would be dry steam. So the dryness fraction is Ms, which you measure later by condensing the steam, upon Ms plus Mw. Mw is the mass of water which you have collected here. Now this is a very crude kind of thing, and the result won't be accurate. One can imagine why. Because what happens is, there could be some fine water particles, they would bypass this obstacle, they won't be collected here, and they would flow with the steam. So you condense that steam and measure that mass of, consider that as mass of dry steam, which could be overestimation. It might contain certain water particles which you couldn't stop here. Okay, so if you use this apparatus, which is known as separating calorimeter, the accuracy level will be low. You will be overestimating the quality of steam. That means you will be you will judge the steam as of higher quality, that means of more dryness, but actually it is not that dry. So it's an overestimation. So what is the way to avoid this? There is an interesting principle that is used. This steam which goes ahead, you can say, before I come to this apparatus, let's talk about that principle. One can throttle the steam. If the steam is throttled, and you know that throttling is free expansion, throttling is also a process where enthalpy remains constant. So if you throttle the steam, you can come across an equation, and you can, if you measure the pressure at which after the throttling, you measure the temperature after the throttling, and you can write a simple equation from which you can determine the steam, determine the dryness fraction of the steam. The principle is very interesting. Let me draw this temperature enthalpy diagram. So this is H, and this will be the dome, vapor dome. The horizontal lines here will be all constant temperature lines. Okay, I need not tell you that. The constant pressure lines will be running like this. So let's say this is, okay, this is So these are all constant pressure lines. So constant pressure lines, as we have discussed in previous videos, they will be they will be along this line, then horizontal, and then they would move like this. Okay. So I'm just removing this line. Okay. So these are all constant pressure lines, and you could immediately see that in the vapor region, that means wet steam region, the constant pressure line as well as constant temperature lines, they coincide. Okay. Now, as I said, throttling is a constant enthalpy process. Imagine that the steam is wet, okay, and you pass through the throttling device. When you pass it through the throttling device, it expands and the enthalpy is constant, the pressure drops. So this is one pressure line, let's say this is P1, this is P2, this is P3. Now suppose you drop this, the pressure is dropped to, let's say, P2, okay. So if you drop this to P2, you can say that enthalpy here and enthalpy here is same. I'll show it by dotted line. The throttling process is represented by dotted line. So, but if you drop it further, let's say you drop it further and you come here, let's say that at point pressure 3, the enthalpy at point, this is point 1, this is point 2, this is point 3. Enthalpy at point 1 is equal to enthalpy at point 2 is equal to enthalpy at point 3. Okay. So if it is we can use this equation. So in a device, all that we require is, you know, the pressure of the steam before it is throttled. Then you want to know what is the pressure of the steam after it is throttled and what is the temperature of the steam. Okay, what is the temperature of the steam? Now say, let's say that we have throttled it to point 2. Okay, but now the problem is here. What you can do is you can equate enthalpy at 1 and 2, right? So I can write this equation, H1 is equal to H2. What is expression for enthalpy of wet steam? It is HF plus XHFG, and this will be at pressure P1. Okay, this is at pressure P1. This will be equal to, I'm equating at this. So this is also a wet region. So you can say HF plus XHFG at pressure P2. Now you can solve this equation. What you know is initial pressure, right? Initial pressure is known. So from steam table you can find out HF. From steam table you can find out HFG, right? So on the left hand side the only unknown is X. On the right hand side you should have all the parameters known, or values of all the parameters. Only then you can find out X, because our aim is to find out the dryness fraction. But on the right hand side, you know pressure, you can find out HF corresponding to this pressure from the steam table. You can find out value of HFG again corresponding to pressure P2, but there is one more X that is unknown, right? So you want to get rid of this X. So what does it mean? It means you need to expand the steam further. Okay, if you expand the steam, let's say to pressure P3, if you expand it to P3 and let's say that the steam becomes dry saturated. Okay, now in that case the equation you could write is this, because enthalpy at 1 is equal to enthalpy at 3, and if the steam is dry saturated at point 3 as is shown here, then you can write this enthalpy as Hg at P3. Okay, it is Hg at P3. That means at pressure P3, enthalpy of dry saturated steam is Hg, and you can find out Hg. Okay, so on the right hand side everything is known. Given pressure P3, you know the pressure enthalpy of dry saturated steam, and then the only unknown is X. However, there is also a problem here. What is the problem? The problem is after expansion, what you are going to measure is pressure and temperature. Okay, and suppose just say that at pressure P3, you can from steam tables you can find out saturation temperature correspond to that pressure, and this dry saturated steam will be at that temperature. Okay, so after expansion, when you measure the pressure of this steam and the temperature of the steam, and if you see that this temperature is saturation temperature corresponding to that pressure, right? You cannot be sure whether the steam is really dry saturated or wet, because the temperature of wet steam is also equal to saturation temperature corresponding to that pressure. So you need to be sure, right? I mean, in principle you can use this equation, but in that case you want to be sure that the steam has really been dry saturated and it is not wet, because if it is wet, it will be, you know that in the right hand side you will get another X. You don't want that. But how can you be sure that the steam is dry saturated and it is not wet? You can't be sure, because temperature of wet steam and temperature of dry saturated steam are same. So to get over this problem, you expand it further, right? You expand it further to lower pressure, and because if you lower it, just see here, if you expand it further, you are entering the superheated region, right? You are entering the superheated region. Let's say that this is another pressure line, right? And see, this is, let's say you are entering here, okay? So there could be some, the shape could be different, but anyway, so we are entering in the superheated region, and maybe I could just take it down the line to make it. Okay, so let's say this is 0.4, and this 0.4, now you have, this is pressure line P4. So you expand it to low pressure. When you expand it to low pressure, the steam becomes superheated, and then it's possible for you to know whether the steam has become superheated or not. How can it be done? You know the pressure, that's the pressure after the throttling. See what is the saturation temperature corresponding to that pressure, and if the actual temperature of steam after throttling is more than saturation temperature, then you know that the steam is superheated, okay? You are sure that the steam is superheated. You can't be sure that the steam is dry saturated, because the temperature is common for wet steam as well as dry saturated steam. But when you see that in the device after the throttling, you measure the temperature, you measure the pressure corresponding to that pressure, measure the saturation temperature, and the actual temperature which you measure, if it is more than the saturation temperature which you have measured from the steam tables, then you are sure that the steam is superheated. Once you are sure that the steam is superheated, then our task is simple. All that you have to do is, on the right hand side now, it will be enthalpy of superheated steam, which you can directly get from steam table, and this will be at pressure P4. You get pressure at pressure P4, enthalpy of superheated steam. You have the right hand side, the only unknown is X on the left hand side, that is your dryness fraction. So by throttling the steam, you can find out dryness fraction by just writing one equation. Now just reflect on this. If you had, let's say, if this point 1 were somewhere here, point 1 were somewhere here, right? That means steam were less wet, it's moving towards right, so steam were less wet, more dry, and you wanted to measure this dryness fraction. Then if you wanted to measure it, you throttle it, and you can see now that you need not throttle, there was no need to throttle to a low pressure of P4, but you could throttle up to P3. And the steam would have been superheated. If you throttle up to P3, the steam would have been superheated. More the drier the steam, less is the pressure drop required to make it superheated. More the steam is wet, think about it, shift it over right, then you might have to go still further down to superheat the pressure. So the calorimeter which has throttling device has to be subjected to very, very low pressure, and that's a problem, okay? So the point, what can you do? You can, first make the steam dry by passing through a separating calorimeter, right? And then the remaining steam, because you know that it doesn't give accurate result, but you have made the steam dry, and then you throttle it, okay? And then this combined apparatus can be used for measuring the dryness fraction, right? And this is what I would explain in the next short video. Thank you.